So we got this. All right, so let's start with the next lecture on NumPy. And before we go on to the new stuff, we're going to recap what we did last time, because it's been already 2 weeks, and I think it's good to recap it. You had the PyBullet on HomePeng last week. You enjoyed it?
Yeah.
It's very interesting architecture, and you can do a lot of fun stuff. So the slides, and it was definitely was an interesting lecture. All right, so NumPy review. Just a little review of what we did last time. You know how to create an array, shape, size, data type, number of dimensions. If you see something that you don't remember or that you want clarification on, this is the time to ask it, because I'll go pretty fast otherwise. So slicing, there are fairly many ways to slice an array. Most important is to set limits at the beginning, at the end, or only at the beginning or at the end, and also take like modulo 2, modulo n slices. You can do slices on multiple dimensions in different ways, and you can also use some particular shortcuts like this one to implicitly say that you don't want to touch the other dimensions that are there. So this is stuff that we saw already. Also, you can slice with booleans, index with booleans. Basically, if you have an array that has the same shape as the array that you are interested in selecting from, and in this array there are booleans like this, then you can just pass the Boolean array into the indexing brackets, and what results is basically the one-dimensional array with the value that you selected, right? So aggregations, you can do, of course, sums along dimensions, but not only sums. You can do averages, you can do mean, it's the same, variances, minimum, maximum, whatever you think of. There is definitely a NumPy function for that aggregates the data along the dimensions that you choose. If you don't specify a dimension, you will aggregate to a number, so it will aggregate across all the dimensions. This. Broadcasting, now this was an interesting topic for the one that never saw this. If you have an array, you can multiply an array to a number, a scalar, and basically this will multiply element by element times the scalar, and you will get, so if you have an array that is a matrix, for example, every element of the matrix will multiply by the same scalar. But you can use it also to multiply array with certain rules. You guys remember what the rules are? Anybody wants to try?
The column of the first.
So let's say you have, let's say you have two NumPy arrays, A and B. When is this broadcast multiplication, for example, not possible? What are the things that will preclude you from multiplying this array with the next? Any ideas? There's multiple of them, so give it a shot. So can I multiply a number times a matrix?
Yes.
Right? Fantastic. What about if I try to multiply vector times a matrix?
They should share a dimension with the same size.
So if you say if this is a vector that is 3 elements and this is a matrix that has 3 elements and 4 elements, it might work. Yeah. Right? But it depends on the conventions. It's safe to say that it's better to make it first a matrix with just one column or one row and then multiply it, right? And what else did I do this that works, but you didn't yet tell me? What else works here? I'm multiplying two matrices, but you can select the pen, apparently, but they don't have the same dimensions, the same size in the dimensions. So why I'm able to multiply them and what's happening here?
The first matrix will be the 3, 4. So the column will copy maybe so for copies.
Exactly. So basically, it's the same that is happening also with the scalars. You are broadcasting this row into this basically four. So this column into these 4 columns, right? And what will happen is that again, this is not a matrix multiplication, right? So this is element by element multiplication. Means that if you have here 1, 2, and 3, and here you have many elements, basically, as you said, this will be copied over, and then this element will multiply with this, this with this, this with this. It's always the same one, but it will be just copied and multiplied over together, right? This is important. When you multiply these 2 matrices with the star sign, it's actually multiplying element by element. If you do dot product, that is multiplying row by columns. Okay, so don't confuse the two, because otherwise stuff won't work. So just to recap, the broadcasting works when the rank is the same, so you have the same number of dimensions, and the dimensions are either 1 or equal, right? So if the dimensions are of size, one dimension is size 5 and the other dimension is size 7 in the same position for the 2 arrays, it will not be able to multiply them. If one of them is 1, it will work. If both of them is 1, of course it will work. That's just the base case, and everything else works. Good. So let's move on. Reshaping. What happens when I reshape an array? So let's say I have a vector 1, 2, 3, 4, 5, 6, and I say I want to reshape this as 3, 2. What will I get out of this?
3 row and 2 columns.
1, 2, 3, 4, 5, 6, right? This is what I get. So the stuff gets basically broken down into the dimension that I specify, and then reshaped like that.
I think it's
0.
It's probably the other way around. Did I make this wrong? So it's 1, yeah, it's 3 rows, yeah. There you go. 1, 2, 3, 4, 5, 6. There you go. Right? So it gets basically broken into the dimension that are specified and then reshaped as that. All right? What is the constraint on what I put here? When does it work? When it doesn't work? Can I put here 4, 2?
There is no 8 elements.
You don't have 8 elements, right? Can I put here 3, 1? No. But I can put here 3 minus 1. What happens then? Remember? So when you specify a -1 as shape, basically in NumPy means that he has to figure it out. If I say this, then I say put whatever you have left as a multiple of whatever product of dimensions came before in there, so that it fits the number of elements I have up here. So if I have 100 elements, I tell it 10 minus 1, it will put 10 columns, right? And so on. All right, so that's reshaping. These little rules, it's just important to memorize them, because you'll see these errors coming again and again in your code when you try to do operations that this dimension doesn't fit. You're trying to multiply a rank 5 with a rank 4 or stuff like that. And this is because of this consistency rules that you have. Good. Ravel and Flatten are basically simple ways to tell reshaping in a one-dimensional vector, nothing else. Stacking and concatenating, basically putting the arrays together. We're seeing this, not much to say about this. And the same token, you can split arrays into multiple arrays, and sometimes it's useful. For example, if you have an array, we'll see array of vectors, and you want to actually create a list of these vectors, then you might want to use this. And dot and matmul, usually it's pretty simple if you have two-dimensional arrays. If you have 3 or 4 dimensional arrays, you have to be careful what you want, because they actually give you different results. And yeah, I usually use einsam because it's easier. Do you remember how einsam works? I don't have it here. Yeah. Well, it's later on. No? I forgot it. Okay. Einsam is this rule that sends basically I, j, k to ik, and then you pass it to matrix A and B, and it will basically contract the indexes with this rule. You can put whatever you want here, and it will basically follow this multiplication or tensor multiplication if you have multiple dimensions, the way you write it down. So this way you can control really well what you're doing, and you don't have to remember the conventions for dot and matmul. All right? So determinant and inverse, you can do this. There's this linalg package. We'll see a lot of this today. And eigenvalues and eigenvectors, also very important. You can do that also with the linalg. So you don't have to bother about writing down this algorithm yourself. It's already prepackaged in NumPy. Today's topic is going to be putting NumPy to work, to do something a bit more interesting. And so I'm going to spend like the next half an hour doing a bit of theory about a particular problem that we have in computer vision, which is matching a model to a point cloud of data that we have, right? So the basic idea is that you got this model of an object, and you have it at the origin, but then you have a 3D camera, and somewhere you have a point cloud, and you want to see, okay, what is the pose of my object compared to the point cloud? So, and there is better techniques nowadays. You can use deep learning. It's a lot more precise, and it doesn't have the problems that we'll see this system has. But for refinement, it's still very much used, even in state-of-the-art systems. And this algorithm is called iterative closest point. What we will start with, though, is how we solve this little step that makes the iterative closest point possible. And this is basically matching the rotation of the model to the point cloud of the data, right? So finding the best rotation so that the model fits well, right? And this is done using a mathematical tool which is called single value decomposition, which we'll see, not in detail because we're not mathematicians, but we'll see how it works. So first of all, each problem of this kind is a least square problem, right? What is a least square problem? Is a linear system of equations where you want to minimize the norm between what is on the left side and what is on the right side. So you basically do this. And one simple way to do this is remembering that every matrix can always be decomposed in the U sigma V transpose, which is single value decomposition again, where U and V are orthogonal and sigma is diagonal. So it has only elements in the diagonal. Now this is valid for n matrices. It doesn't have to be a square matrix. And in this case, sigma will not be an invertible matrix. It could be, for example, for a 3 times 2 matrix, it cannot be invertible. It will have one column of 0 if it's only diagonal, right? But it can be pseudo-inverted. You can find the pseudo-inverse, and we will use it. For the case that we usually have, this M and N are the same, and then you don't care, right? But the general case is here. So why is it interesting to split it like that? Well, the idea behind the single value decomposition is that if you have this, well, you can create the inverse. Let's call it the inverse and pretend these are square matrices by simply doing taking this matrix and thinking, okay, if I want to multiply this one and create an identity, what I would do, right? I have U, oops, I have U and then sigma, which is diagonal, and then V transpose. So these are orthogonal. So to eliminate this, you take U transpose. Because U transpose orthogonal means then U and U transpose multiply into the identity. This is clear, right? Okay, so sigma, well, sigma, you take just sigma to the -1. It's a diagonal matrix, so you put all the diagonal elements with the inverse, 1 over the diagonal matrix of the original thing. And this also eliminates this, and you still get here an identity. And then to eliminate the last one, you just take V, because V transpose is, again, the identity. So you found that this matrix is the inverse, or the pseudo inverse in the general case, of this matrix. And now you can use it, because then you can put, here, you can do this. This is 1, and now you find the x, right? And this is basically how you solve the least square method in general with this simple method, right? But the problem is, this is not what we're trying to solve when we align a model, because we're not trying to find the points. This would be the points of our model. This would be the points from our sensor, for example. We want to find the matrix, right? We have a different problem here. And the matrix has a particular property. It has to be a rotation matrix. So it has to be an orthogonal problem. So that's why we are looking not at that problem, but what is called the orthogonal Procastus problem. Procastus was a philosopher, and if you look at the Procastus problem, you'll find in Wikipedia there is a slice man trying to fit in a bed. It's basically about fitting stuff into stuff, like making things align as much as possible. And in this particular variety for the orthogonal one, you're basically trying to find the best rotation that will minimize the difference between the rotated point A and the points in B. Now, A is a matrix with all the points that you have from the model, basically, as lines. And B is a matrix that will represent all the points from your sensor as lines in this matrix, right? And when you rotate the points A, then you will get something that, if you rotate it well, probably minimize this norm. And it's clear that this is what you want to do, right? You want to minimize the distance between the points in the model, the points in the sensor, so that the model is aligned to your perception. Is it clear so far? All right, so now the rest is a bit theoretical, and I won't get into the details of it, but basically this one, which is called the Frobenius product, is basically the trace of the product of two matrices, okay? It's trace AB times B. And it has certain properties. And if you look at basically what you're minimizing, the norm, the square norm of the difference, you can turn it into the product of this and this as the Frobenius product. And then you basically take the square part, which is irrelevant because it doesn't depend on the orientation. It's always the same. You take it out and you maximize this part because you have a minus sign. So you turn this problem into this problem. And once you do this, there is a bit of magic basically by using properties of orthogonal and trace, orthogonal matrix and trace of products, and you end up with this problem. Maximizing U transpose V, basically you rewrite A as U sigma V transpose, then you bring U transpose on the other side, V transpose on the other side, and then you maximize this thing. And if you call S this matrix, now S is orthogonal because U is orthogonal, omega is orthogonal because it's our rotation matrix we want to solve for. V is also orthogonal, so this is orthogonal. And this is the sigma, is the diagonal matrix with the only the eigenvalues. Now, what is the maximum with an orthogonal matrix and a diagonal matrix? It's always the identity. Because if you think about it, the matrix, the orthogonal matrix, can only have one as maximum on the diagonal when it's the identity. Otherwise, it's going to be a cosine or a sine of some angle, right? When you rotate it outside of the identity. So when you go and multiply S by sigma, which is only diagonal, the best that you can have is that you have the full eigenvalue and not a fraction of the eigenvalue in the diagonal. Then when you create the norm, you take the squares of those eigenvalues. And so therefore, the maximum of this expression is for sigma, is for S equal to the identity. But then if I have this, and I call this the omega that solves this argmax, right? I invert this equation and then I have it. The rotation, the best rotation that I can get is U times V transpose, right? Make sense? It's a bit theoretical. You can see the details anywhere, any linear algebra book or Wikipedia. Good so far? Good. So once we have that, then we can do the following thing. We have, so far we just spoken about the rotation, but I have another problem. I need to bring the model to where my sensor has discovered this object, right? So the first thing I want to do is I want to align the centers, right? So I have some data here. I want to bring my model here, and then I first rotate it. Okay. When I rotate it, first then I match the point, the closest point to each point of the model, and from the sensor and vice versa. So I match points the nearest of one another. Okay. Once I have matched them, I minimize the square distance. So I solve the single value decomposition, I do a rotation, I align it. Now I align the centers again because I moved the model. So, well, the center is still aligned unless you have a partial observation. But then I match again the points and solve the SVD again. Rotate, match against the points, solve the SVD, rotate, and so on. When do I stop? Do I know if my matching is precise? Well, I could, but usually what you do is you look at the residual correction. If you can't get any better, then you're either stuck in a local minimum or you solve the problem. And what can happen is that, pretty simple, right? I mean, I could say, well, this is the perfect pose, but if I'm here, I will not get out of this minimum and get this pose, right? Because the alignment, it will go through a higher error in the alignment, in higher sum of the norms of the distance of the points when I match them before I get to the right place. And this is the problem with iterative closest point, mainly, right? So far so good? All right, and let's look at a bit of code. And we'll start, remember how to do this, with single value decomposition. All right, so here I have created 3 points, and then I'm just doing some shifting to get them out of the way so that I can use the single value decomposition to basically find the matching points again, right? So I first add some translation, fixed translation 555, and then I create a random angle and I rotate them again around the z axis, right? So cos theta minus sine cos around the z angle. Is clear why this is rotation around the z angle? Everybody? Okay. So once I've done that, just multiply my matrix for the points, get the points outside. So now I have my original 3 points, and then I shifted them, I rotated them, and then I'm asking my single value decomposition how to bring this back to that. Oh, actually the other way around. How would I bring this to those? So I want to try to replicate the rotation matrix. So first I calculate the centroids, take the mean of both, and then I shift the points to the centroids. So basically I'm left with this. Why do I do this? Because I want to basically center both points at the origin. Right? When I center them both at the origin, I have only the rotational matrix to act on. Right? So when I remove the centroids, then I can take both centered one and create this matrix, which is A transpose B. And if you remember from the presentation, let's see, this is the matrix BA transposed. Oh, it's conveniently circled. The matrix BA transpose that I actually single value decompose here. Right? This is our covariance matrix. This is our covariance matrix. And it basically is the tool that I use to do the single value decomposition. Now, I don't need to do anything else because the single value decomposition is already implemented, so I don't need to do any calculation of the sort. Lineage does it for me. And once I have that, I get UVT, I multiply them together. Oops, sorry. I multiply them together here. So I get my rotational matrix. This would give actually the sigma, but I don't use it, so I ignore it. You remember what this symbol is, right? If I don't want to use an output variable, I just put underscore so that the editor doesn't complain. So I can multiply them. The translation is going to be this, this expression. Remember that on one side I can just directly translate, but the other side I have to rotate it first. Right? If you remember when you, did we do this? When we invert a rotational translational matrix, I think we did it in one of the first lectures. If you invert a rotational translational matrix, which is basically this object, right, with one column, 3 by 3, and then 0, 0, 0, 1, you get r minus 1, and then you get, if I remember correctly, minus RT, 0, 0, 0, 1. Okay, so this is basically what you're seeing here. And on one side, since you are going in the inverse direction, you have to use minus RT. Okay. So this is the translation vector. And well, then I can print the result and plot it. Is it clear what I'm doing here? All right. So what you see now is the original points that I created, the target points, and what happened by aligning them in one step. And this, you can have fun because there is a random rotation, so it works all the time. Because it's a closed solution. You're not guessing, you're not iterating, you're not doing anything. This is, the best solution is there, and since this is a precise rotation of the same pattern, I can solve it without any error, right? And the single value decomposition will give me the precise solution to this least square problem right away. Right? So by the way, the plotting, I hope you guys have had some experience by now with Matplotlib. Did you guys try something with Matplotlib? It's really useful. Whenever you have to visualize things, it's a godsend. This is, for example, here. Let's delve into this because it's quite interesting. So when you're dealing with point cloud, what you want to do is you scatter plots, and then what you can do is you can do these subplots with projection 3D, and it's important to remember to set the limit yourself, because otherwise it will stretch and you will not recognize what you're doing. So, but the interesting part is this. So if you want to print a 3D picture with your points from whatever calculation you're doing in NumPy, you just select the vector of the x variables, a vector of the y variables, a vector of the z variables, and then you print them all like this. This will create the scatter plot that you saw with 3 points or with 1,000 points, you don't care. This is a vector of like 1,000, right, times 1. I just remove it, actually, just 1,000. And this contains all the x coordinates. This is all the y coordinates, this is all the z coordinates. It's not the list of the vectors, it's just the list of the coordinates themselves. which is a bit counterintuitive, but I think it's better because otherwise you have to list a lot of stuff here, right? So in this way you have only three vectors. Then you can then do whatever you want. You can color them. You can put specific, dots, markers. So you can put more of them inside. You can do a lot of things. You can put scatter plots on the same plot. I did it on different plots because I like to see them separated, but you could put all these scatters on the same AX1 on the same subplot. Then you can see, for example, the red is your model and the blue is the sensor data, and see how it matches, right? Or you could put it on top of any picture. That what we do, for example, when you do computer vision and we recognize a model on top of the RGB picture that we take from the camera, we project exactly the scatter plot from the model on top of the RGB, so that we see if it matches with the picture that we took, right? That is a very quick way to visually see if your algorithm is working correctly. Because when you look at the numbers, you can really imagine, but we're very quick to see if the point is outside of the object or not, right? So again, visualization, absolutely top important. So learn Matplotlib if you're working with this kind of data, with 3D, 2D, or any sort of visual data. Okay. So let's consider for now a different problem before we go on with the demo. Usually, when you have a camera, it doesn't precisely give you, first of all, the whole model. This is probably will not do it. It will only give you one side, right? Because you're looking at it from this side, you will not see the back part of the model. So that's one problem out there. But there is another problem. Even if you have multiple cameras and you can monitor it from every side, which some people do, you have 3, 4 cameras, even from the back side or whatever, still the camera has noise. So any 3D camera you see around, or except for a 3D scanner that we have in the lab, will have a couple of millimeters of noise when you start acquiring data. Now, you will not be able to solve this problem exactly with one go. That's why we do ICP, right? And even then, it will not be precise, right? And the matching is not perfectly clear. So there is a lot of techniques that you can use to clean up your data, to try to remove variability or frequency that is, that is part of the camera and not part of the object, because maybe the quality of the object, so you know that it doesn't have this kind of frequency in the features of the surface. So you can try to remove this. You can try to engineer a lot of pre-processing before you do ICP. At the end of the day, you still have the problem that you have a noisy sensor, right? So that we saw before doesn't work. So what we are doing then, let's try to simulate this noise. What I'm doing here is I'm generating an asymmetric object. This is a hook, basically done like this. Okay, and it has some width, so it's like this. And the code that we use here to do it is quite interesting. I want you to look at it for a while, because it shows you how to use, for example, new axes and broadcasting to do interesting stuff. So what I'm doing here to generate all this, I first generate two things. This line, the center of the hook, and this line, the center of the straight part of the hook. So it's two different routines. And the first one is basically generating a set of angles with a lean space. Do you remember the lean space? Lean space takes a start, an end, and then splits it into how many steps you say, in this case 50, right? And I take this from 0 to pi, so from here to here, right? So then I want to create the centers. Quite easy. I take the radius, multiply the x for cos theta, the y for times sin theta, and I take z to be 0. So I do it planar, right? Like this. Make sense so far? Now, what I want to do, at every point where I am, I want to draw another circle around and basically extrude this circle around a cylinder, right? Does this make sense, what I want to do? So I start with a circle here, and then I move it like in my direction, and I keep sweeping the space with the circle to create this tube that I want to generate, right? So how do I do that? Well, what I want to do is I want to generate for each of these points that I sampled, here's 50 points that I sampled, I want to generate the circle and then add it on top of the center. Make sense? So how do I do that? Well, I just say I leave a new axis free so I can play with, right? So my center points will be labeled by the axis 0, and the points around the center points will be labeled by the axis 1. Make sense? And this is what I'm doing here. So I'm creating a new set of angles from 0 to, well, the one stop before 2 pi, right? 9/5 of pi. And I'm creating 10 steps. So basically, if you go around the circle, I'm doing 1, 2, 3, 4, 5, 6, 7, 8, 9 angles. And then I'm creating my radius coordinates. So the radius coordinates are going to be different depending on where I am in theta, right? So when I'm at the beginning, theta is 0. I'm around the x-axis. I'm revolving around the y-axis in the x and z, right? But when I'm turning theta and I'm at 90 degrees, now I'm revolving around the the x-axis, and I'm going into the y-z plane, right? So that's why I need, in the x, I need the cos of the original angles times, or the new angles times the cos of the original angle. So when I am at zero, this will be 1, and then I'm just rotating with the new angle around the center of the tube. But when I'm at 90 degrees, this will be 0, so it will not move around the x-axis, right? The contrary happens on the y. I start with the sine, so it doesn't move on the y-axis at the beginning, but when I turn 90 degrees, it then rotates around the x-axis and moving the y-axis, right? Does it make sense? Right? If I rotate around the x-axis, it means that the y-axis is actually changing. That's why the sine is actually 1 at 90 degrees. And for the z-axis, I don't care, because it will always go up and down on the z-axis wherever I am. So why this works is because of broadcasting. I don't care about the indexes. I know that it will multiply all my center points from the first dimension with all my angles around the tube from the second dimension, and will generate my 50 times 10 points on the curved tube. Make sense? Remove these comments and I'll let you stare at it for a while. And you tell me if everything is as you would expect it, or there's something that bothers you. Most of coding in NumPy is like this. You figure out what your problem is, and now you try to fit the dimensions so that you actually get out of this computation. How? What would be the obvious way to program this without thinking about extra dimensions and broadcasting and everything? You make 2 for loops, right? 4 y in angles, 4 z in theta, and then you multiply. And then you add it to an array, and then you create the array from that list. And why we don't do that? Because it's slow, right? When you do it with 50 points, you don't care. But when you do it with 5 million points, for example, in a 4K image, you do something like this. You want to rotate the color space. You have fun doing it in a loop. It's gonna take forever, right? So never do it if you can do it with NumPy. But do it with NumPy means you have to start reasoning about, if I want to multiply this by this, and I want to multiply all of the elements, then I need to make space for a new dimension. so that I can fit these elements from the second array into this new dimension, while I keep the array, the elements from the first array in my former dimension. And then I can multiply them all by all, right? Because of the broadcasting again. Make sense? If you have doubts, you tell me. All right, so once we've done that, well, the same trick we can do also for, I'm getting confused here with this. The same tricks we can also do with the straight part, which is a lot easier, of course, now, because what we do is generate the centers. It's so we started from 0, right? And we went in the positive direction. So I want to generate the straight part from the negative side. So in this case, I start from -1, I generate 10 elements and stop at -1. Sorry, -10, I generate 10 elements and stop at -1. Should be 9, actually, it's nicer, but no, it should be 10, because I'm taking the first and the last. All right, so anyway, it's just because it's nicer to read the numbers in the matrix. It's not really, it doesn't matter. Then I need to rotate around these centers again, right? And create these circles of radius 1. But this, in this case, is a lot easier because I just know in which direction it rotates. This is along the x-axis, I think. So basically, exactly, the radii, they only go into the x, this is along the y-axis, of course, because I'm along the x-axis at the beginning. So the radii, they rotate only in the x and z axis. They rotate around the y-axis because the line needs to go along the y-axis, right? So I rotate this with cos and sine, and then again, I just stack them together by adding them with broadcasting. Because I add the center point that is along this line times the circle, but since I broadcast them, it gets added to each point on the center. And then I get out of this 10 plus 10, I get 100 points with broadcasting again. So when I run this, let's see. Let's do this step by step. So we have generated points, and we can just plot them. Let's run this here. Yeah, 3 times. Sorry. I don't want to change the code now. Oops, they forgot all the parentheses. How about that? So, and this is my hook. Right, so the straight part and the circle. Plot 3 times, very boring, like this. So now the question is, how do I rotate this stuff and add noise? Because I want to simulate my sensor. So the idea is that I first rotate the whole thing with a rotor translation matrix in a convenient way, so I can process it in a batch. And then I add random noise to each point in my model in the rotated part, so that I can then pretend that this is my sensor data and I can perform ICP on top of it, right? So this is right here. So first, okay. So can somebody tell me what I am doing here? Volunteers? Because otherwise I'm always talking, and you also to talk a bit.
There are 3 rotation matrix along the y and x axis, and
Yes, so these are three rotational metrics, one around the z-axis, one around the y-axis, one around the x-axis. And what am I doing with that?
So first, rotate along x and then y and then z.
Right, this is the shortcut for matmul in NumPy. You can use the at. It's a very convenient operator. I'm randomizing them, right? I'm taking a random angle, creating a rotational matrix with the standard formula cos minus sin cos. In y you have to leave an empty cross in between, and then in x you go on the last part of the matrix and do the same as for z, but leaving the first row and the first column empty, right? This is clear why this is a very rotational matrix, right? If not, tell me, then I mean, the rotational matrix, right, operate by rotating the components of the vectors in this particular way. So if you figure out that here, ignore the rest of the dimension. Let's pretend this is just a 2 by 2 matrix, right? If they operate on 1, 0, then basically you see that cos theta times 1 will generate basically the diminished side on the main axis that has been rotated, right? And if you operate on 0, 1, you will see that it generates then the part that appears because the unit vector has been rotated on the other side, right? This is why this is a rotational matrix. If you want to build an intuition, just always think about rotating the unit matrix, the unit vectors. This will tell you what's going on with this. And if you think about it, you can read here where the unit metric goes. The first unit metric, so unit vector goes. And here you read where the second unit vector goes. Right? If you have like 1, minus 1, 0, 0, right? Well, this is basically here, and this guy goes here, right? You see, you can read the rotation from the components of the matrix directly, right? So it's a lot easier. Just instead of looking at the math, just look at the matrix. You see the versor, and you know where the rotation goes. Okay, so I need to stop zooming on two sides. Okay. So I have rotated the matrix, and then I just add some random normal noise. This is another interesting feature of NumPy. You can use different distributions of directly from random. You can sample from random uniform, from random normal. There are other distributions you can use. So if you need it, just look at the documentation. You can, and it's very efficient in doing it. In this case, I sampled from random uniform to create a translation because I want it to be equally probable in all the whole space that I'm considering. But I sampled from random normal to create the white noise around the point position. Right? So is it clear what I'm doing here? I'm first translating the object with a random vector. The random vector can move me anywhere in a 5 by 5 cube, basically, so 10 by 10 cube around where I am. But when I want to add noise to my detection, basically around the point, I don't do a uniform noise, right? This is the typical sensor noise you model with the normal, because you assume that is caused by independent causes that sum up to create a normal distribution. That's why you usually model it with a normal. This is no sensor noise. This is just me figuring out that I usually don't have the object here, but it will be somewhere in the space, right? It's not a sensor problem. So that's why it's random uniform. So now I add this random noise to all my points, right here, and I return it. And this will create a new hook somewhere, which we're gonna see. So the hook is function. And you see it's a bit wobbly. And it generates random position, and the shape is also a bit, wobbly in different ways. I mean, you can play around with this kind of stuff and see how much the normal noise actually influences this. Where did I put the parameter? Sigma. Let's put it at 1, for example, and then it's it's very noisy and so on. I mean, you can again, this is very useful thing that you should learn as a tool whenever you're developing an algorithm or technology or hardware even. Having the possibility to quickly generate test data by just randomizing stuff and thinking ahead of what could be the situation where you test it. You don't need to actually acquire the data from the real sensor. But if you have an idea what kind of noise you're dealing with, what kind of situation we'll be dealing with, you can generate random data and just test your algorithm quickly. A proof of concept, right? Doesn't cost you anything. You can generate as much data as you want. And by changing the parameter, you can look into different situations. Sometimes you can even train in your network, for example, or an algorithm with optimization on synthetic data if your model is good enough. You don't need actually even the real data at all. We do this in computer vision and grasping with the robots all the time. All right, so now we're going to look into the full ICP implementation. And solve this matching problem. But first, let me comment out this so that we don't get the plots every time. All right. So this is almost the same as we had before, with a bit more control and a bit more documentation, let's put it this way. So, I mean, I don't have to go over this. This is the same single value decomposition we had before, right? We first match, I mean, this is new. We first match the objects, the points across from our target and a source copy. Okay? So what we do here is basically, again, we create a new axis, we create the norm between all the points on the source, all the points on the target, and we create the norm matrix here. It basically tells you for each point which is the nearest one here, right? And in this column also for this point, which is the nearest point from the model, right? So when you want to match them, you have to take the minimum either on one side or on the other. You decide which one is the most meaningful in this case. So in this case, we do it on the first axis, right? Take the argmin of the distances, closest index, and then closest index, we use it to slice through the target and match it to the source, okay? So the closest point from the target is given by the argmin of the distances. Make sense? Again, this is something you'll see a lot. You first take the argmin. What is the argmin? I didn't tell you. So if you have, for example, here, 0.1, 1, 15, 0.02, 0.3. The argmin is the index of the minimum. In this case would be 0, 1, 2, 3. So that's the argmin. And if you have the argmin for this matrix along this dimension, then it's basically 3, 5, 9, 0, and so on. The indexes of all the minimum elements in the columns. Make sense? Right? So we first extract this argmin, and then we plug it back into this part, right? To get the targets. And we get a copy of the target for each index. So we take first the third, then we take again the fifth, right? And so on. Then we put the third here in the first place. Take the fifth and we put it in the second place. Then we take the ninth and we put it in the third place. So on. right? And we create a vector, and this vector is our closest points. Oops. Good so far? Any question? Then let's move on. The rest is the same. We find the centroids, we remove the centroids, we do the composition of the covariance matrix. We get U and VT, and we find the rotation, and we then perform, we find the translation by using the centroid target and minus R centroid source, right? Because of the inverse of the rotor translation transformation. And then we apply the transformation, and there we go. And what we do here is we check for convergence. So once we apply the transformation, we look at how far it is from where we came from. And we look if the previous error is almost the same as the current error, not moving anywhere near, so I can stop. Or otherwise, I stop when I completed 100 iterations. Why did I put this in here? And why it's always a good idea to put it in if you're doing something like this. Any idea? What could happen if I didn't have this? If I just had while true? I go through all this code, right? And then I check if the error is the previous error minus the current error. I assume that the previous error was actually bigger. Is less than the tolerance, that basically how much I want to improve by each step. Could it be that this is always false? It's not an obvious question. Eh? I'm not fishing for yes. It's not always. So I'm starting with a big error. Let's say I start with an error that is like 10 centimeters. Absolute mean absolute error between the points of my model, the points of the detection. Again, I reduce this to 1 centimeter. Say that my tolerance is 10 to the minus 6. So it's pretty low. I keep reducing it. If the mean error is greater than the previous error or around the previous error, and I mean, let's say if I go from 1 meter to 1 meter, right, I break. Because I'm checking the difference between the two. If I go from 1 meter to 2 meters, I don't break because I'm taking the absolute value. So if I have some bistable system that basically increases the error, that decreases the error, then increases the error again, because my model is not alignable with the sensor data, I might actually run this forever. If my tolerance is too low, and it's basically, let's put it this way, if it is of the order of magnitude of the sensor noise, it can be that I start realigning the object back and forth, because given one state, it will prefer to go in the second, and given the second state, it will prefer to go in the first. You're not guaranteed to find a minimum, even in the local minimum. So it's always a good idea in these cases where you have an iteration that relies on a condition to stop, to always put a plan B in motion. If everything goes wrong, at least I stop at 100. Can put it at 1 million, but at least it stops, right? Otherwise, it'll just run on forever. Then you have to kill the process. So we find that it's below our tolerance or that we have run 100 times, and then we're done. Now we print two things. The first one is the ADD error, which is basically this guy over here. We match, in this case though, every point to the corresponding model point. We assuming in this case that we know what points from my sensor belong to the points on the model. Does it make sense what I'm saying? No, I'm not matching the points first. I'm just saying I know that this point from the sensor is my corner here. So even if it's like this, I'm matching it to this corner because I know where it is, right? So this is actually, you do this when you have a ground truth. You do it as validation on your ground truth. Because if you have a sensor and you're trying to understand if it works, you cannot do it. But if you have a sensor plus somebody told you that the phone was aligned in this way, and that is the corner, then you can check for the ground truth. You can check if it's misaligned or anything else. It doesn't help you with stuff like this. Why? I mean, ignore that there is a little writing here. Consider that there is no other feature, it's just circular and cylindrical. Why I can't do this? What differentiates this point from this point? Anybody? Let's put it another way. How would the camera know without the label if the pen is rotated this way or this way? Would it be possible? Are you able without the writing to tell me if I rotated it or not? If you close your eyes, I rotated, and then you tell me, did you rotate it? You don't, right? So the same happens with the sensor. The sensor is not able to detect if it rotates or not. So if you have this as validation, that knows, that this particular atom in the pen has to be aligned to this particular atom in the perception, you are screwed because you're not going to be able to optimize for it, because you're not going to be able to observe this difference. And if you're not observing it, you're not going to be able to optimize for it. Whether it's a neural network or an algorithm, whatever you come up with, you're not going to be able to do it. So that's why people come up with a different method, that is the symmetric, average symmetric way. And it's basically, you match the points of the model to the point of the sensor, you match the point of the sensor to the point of the model, you calculate both mean error, and you take the average of that. And this is what we do in the second case. So, I mean, the formulas are not that page turners are just here. If you want to look at them, I actually will also upload this to GitHub and share all the code until now from the lectures, including this. Now it's getting a bit more complicated than before. So once we do that, we just print the result and we see what's going on. So you want to see it in action? I do. All right, so, oops. We have already an interesting case. So what happened here? Somebody explained me. So this is our original. Then we move it and randomize it. And then we ask ICP to do this job for us. And it turns out with this. It says, this is the right alignment for it. Is it the right alignment? Is it a good solution? Why? Come on, it's flipped, right? It's flipped. Why is it flipped? What happened? You see the straight arm is here. It's on this side instead of this. This is, you would need a different 3D option, but basically what happens is that somehow this is a typically problematic system for an ICP, because you have, if you are aligning this object, okay, to this object, you have two minima. The real one, the absolute minimum, which is aligning basically this way. Okay, this is the absolute minimum, where you get the least error between matching points. But if you do it, if you are somehow near to the other solution, like this, you will never end up with this system. You will align it something like this. You will, because you are nearer to that solution. It's like when you're flipping the phone, right? You will never be able to get out of that minimum to get the right solution. Does it make sense what I'm saying? What could be the solution? What would you do if you had a problem like this? You have this algorithm, you develop this algorithm, you spend 6 months of your life, you want to publish a paper on it, and it doesn't work. What would you do? Or you're an engineer trying to solve this problem for your company. Any ideas? There's a couple of things you could think of without knowing anything about this. So think about what causes the problem. What is the reason that I get into this alignment, the green one instead of the yellow one? If I have, let's start with this. If this is my sensor data, okay, and this is my model initial alignment, will I run into this problem? No, right? I won't, because it's very simple. Once I translate this, it's almost done. And the minimization will bring me to the right solution. But if I start from this one, I will definitely run into it. So how can I solve this problem? Let's say that this is my model and this is the data that I have. What can I do to not stay in this situation and actually give me a chance to be in the right situation? What could I do? What do you do when you have a USB plug that doesn't go into the computer? Have you ever tried to put an USB plug without looking at it inside the laptop? Right? You don't look at it, you just press on it and it doesn't work. What do? You flip it, you turn it around. You don't see actually what's going on, but you try a different position, right? So why not do it here? Well, the translation doesn't matter because it's aligned directly, but the rotation is relevant. So what you can do is you can take the model and rotate it a few times and try again. If you rotate the model like 10 times, brute force it 15 times, 20 times, 50 times, I don't care. You take this model, you rotate it 50 times, and then you do ICP. What you will end up is with several possible alignments. Now you can apply ADDS, for example, the symmetric measure of the error. And which one do you choose? The one with the lowest error, right? And now you have definitely a solution that is working. So this is also something that is not very intuitive when you start working with this system and with data. But randomizing, it's a great idea. And it usually solves a lot of problems. So if you don't find an algorithmic way to solve the problem, think about try now. Sampling. stuff, and then checking, sample, check, sample, check, sample, check. You get a better solution, throw away the one that you had before and go on, right? Can solve a lot of problems like that. My master thesis actually was something like that. I had to sample basically in higher dimensions several objects to find out which one was fitting. I remember as a student, I wouldn't have thought about this solution if I wasn't like pushed into this direction. Anyway, so this is one way to solve it. There is another way to solve it that uses different technology, of course. You could say, look, and I'm telling you this because you probably wouldn't come up with the idea, but if you have a machine learning system like object detector, right? You could figure out that how the object is more or less posed, but not precisely. So what you can do is have like a two-stage system where you have like a non-precise but intuitive way to find out how the pose is, more or less, and then use the algorithm to refine it, to put it really like millimeter perfect into pose. This is what a lot of systems out there do. They just use a neural network to have a shot at it, get more or less how it's posed, because the neural network can figure out where the features are more or less and align it properly, but not very precise. And then you use, as a second stage, you use ICP to move it into place, precise. Does it make sense? Right? That's a different way. But anyway, I wanted to show you a few cases. For example, in this case, it's perfectly aligned. In this case, we don't know because it's not from an angle where we can see it. In this case, it's not, again, right? So it's really a bistable system. And it is a matter of luck of where you end up with before starting the alignment, if it's aligned, if it aligns or not. And if you don't have this sampling mechanism, it won't work. It won't work reliably. All right? So time is almost up. We will stop with NumPy next lecture, and the lecture after this is going to be on TensorFlow. We'll see a bit of, first of all, as we did for NumPy, we'll see a bit of how TensorFlow works and what it is and what we can do with it in the next lecture. And then the lecture after, we're going to look into a few basic examples of machine learning and how we can implement it on top of TensorFlow. And then the last lecture is going to be on distributed computing, just to give you a few tools that you might use in your future when you have to deal with this or that. You know, oh, I learned about TensorFlow there. Might be it is a solution. You're not supposed, of course, to go deep and to understand all the details of all of these tools. It's more about giving you a library where you can look into if you think that this problem matches that solution. Then you can look at the documentation. But if you don't know that the solution exists, then it's hard to do it. Okay. Any question about this or about the course in general? Good time to discuss it. Since we have 5 minutes. Otherwise, I will check the proposal for the projects this week, next few days, and grade them. Usually, if it's not a disaster, it's going to be a pass. And then we can discuss about the project when you present it. If you didn't yet send the proposal for the project, the draft for the project, tell me quickly. Send me an email. Tell me now, whatever. And let's discuss this. I hope everybody has sent it. I didn't yet look. All right. And let's stop the recording. And